So as you can see on page 299, we begin with what's called Introduction to Stoichiometry. And you've been doing some applications similar to that before today, just in a different manner. And I'd like to think that we may have said when we get back here in January, when we start this stoichiometry, that this is, you could say, my opinion, the entire backbone of what inorganic chemistry is. Okay, and it's not the first time we've heard of that term backbone, right? Why today? Learning about fish. And if you remember from last year, it was called Before the Dinosaurs, that what had happened is when animals in the sea, starting with that of the fish, developed the first type of a backbone, which had a spinal column in it. And what that did is that a type of I want to say endoskeleton, in other words, with grows within. So when we talk about the entire backbone, it's something that's really, really important, and that's what we would consider this information. Not that anything before this was not important. It was. It's leading up to this point. Okay. The reason we say that is on page 299, where it talks about, in that first paragraph, much of our knowledge of chemistry is based on careful quantitative analysis of substances involved in chemical reactions. Now, when we talk about quantitative analysis, we've done something very similar to that last semester, and that was what type of analysis? Not quantitative, but I think we maybe only had it written over there once. It was called qualitative analysis, and what that is, there you're identifying a substance, and that's what you individuals did. But in quantitative analysis, you're identifying what it is, but also how much in a specific quantity. Okay? And notice it talks about chemical reactions. We have not done that yet. That's what we're going to start today. Because composition stoichiometry is what you learned in chapter 3, where you're taking, let's say if you had 15 grams of sodium. We said you're going to change that grams to what probably? To moles, and there you would stop. It's a composition of just that compound or that element only. Okay? So in other words, this composition stoichiometry deals with the mass relationships of elements in compounds. Then we took that one step further and would have said if you had 80 grams of sodium, what's the percentage of sodium in sodium bicarbonate? Then you're converting that to moles or a counting substance of just one element in an entire compound. So we took this in different types of phases. Now the only difference is going to be we're going to involve a chemical reaction because we've only done composition stoichiometry. Where it talks about reaction stoichiometry involves the mass relationships between reactants and products, okay, in in a chemical reaction. Reaction stoichiometry is the subject of this chapter and is based on chemical equations and the law of conservation of mass. Now, that's something that you've always been taught. Yeah, you can't, when you start with one substance, you need to convert it to another. You're not creating more mass. You're not destroying more mass. And that's essentially true. And I believe it's probably always debated that, okay, if you're burning something, even with that exam, if in another class, maybe not this one, you just totally bombed an exam. You say you want to burn it, and it's going to happen. When you do go off to college, okay, tech school as well, I think you would agree, it's going to get more difficult, and when that happens, when we're so, let's say, and you're good students, which you are, you're not used to maybe getting a B on your report card. How many of you, if you had received that would just put you into shock? Okay. Now, will it happen? Maybe. I don't know. just keep that in mind, because I think you would agree the further you get into your sorted career path, the more difficult it's going to be. All right. So regardless, you burn that exam, you say, wow, I had about 5 grams of paper, now it's all gone. I must have, I burned that, so where did that extra mass go? Well, as you're burning something, we know heat is given off. So as you're also doing that, any combustion reaction, what do you remember from last semester? If you are burning a hydrocarbon with oxygen, you're going to produce these two substances, carbon dioxide and water. So even as you are burning that, the amount of paper is getting smaller, but the amount of gases that you're producing being let go into the air is going to equal that of what you had burned from your original paper. So that 9 grams of paper then gets transferred to, I don't know, 7.5 grams of carbon dioxide. Okay, because you're not always going to get a 100%, let's say, reaction rate. And that doesn't mean anything to you right now, but we'll explain that on the next page. Okay, so what we see here, so law of conservation of mass. All reaction stoichiometry calculations start with a balanced chemical equation. This equation gives the relative numbers of moles of reactants and products. So now, again, you're not just dealing with one side of an equation. Now you're dealing with both sides. So reaction stoichiometry problems. The reaction stoichiometry problems in this chapter can be classified according to the information given in the problem and the information you are expected to find, the unknown. Okay, so rather than reading through all that material, the 4 types that we're going to be dealing with, for instance, when you look at what it says about Friday, it says mole to mole and mole to mass. So in other words, problem type 1, given and unknown quantities or amounts in moles. Then what you're going to do is notice it says in that problem, it says amount of given substance mole in an arrow, which means something's being produced, and also says an amount of an unknown substance in moles. You're converting moles of a reactant to moles of a product. That's one type of problem. Problem type 2, notice it says amount of given substance in moles, then an arrow to the right, amount of unknown substance also in moles, but then it says mass of a given substance of that unknown. So there you're converting moles to grams, and we mean that's the same as mole to mass. It means the same thing, it's just saying it in a different manner. Okay. So as we turn the page, then you also see mass of a given substance where you're converting it to moles. And then finally, the most complex of all these first types of problems is a mass of a given substance converting to a mass of another substance using a balanced chemical reaction. Okay. Is anybody thinking, oh my gosh, this sounds terrible so far? Okay. So the mole ratio on page 300, written in green there, says solving any reaction stoichiometry problem requires the use of a mole ratio to convert from moles or grams of one substance in a reaction to moles or grams of another substance. A mole ratio is a conversion factor that relates the amounts in moles of two substances involved in a chemical reaction. Now that probably doesn't mean anything to you right now. Just keep in mind that a mole is just a counting unit. That's all it is. Don't get hung up about all these fancy terms. And one of the things that we had said in class is when this desk was made, I think we've used this example before, how many of you would rather take a tape measure, go across here, and always do your calculations in 96 inches? What's a better way to relate that 96 inches? In how many? Do we know? How many feet? Someone said it. 8 feet. So dealing with the number 8 as a counting unit for 8 feet is going to be much easier than dealing with 96 every time. I think you would agree because the number's smaller, right? Yeah, and that's all that moles are. It's just a counting unit. Don't get hung up on all these fancy terms. It's just a number. That's it. All right. So, as we continue, a mole ratio is a conversion of a factor that relates amounts in moles of any two substances involved in a chemical reaction. Did I just read that twice? No? Okay. So, for instance, what it's trying to show you in that little example with aluminum oxide, what type of reaction do you think that is? It says 2Al2O3 and an arrow where you have Al plus O2. What type of reaction do you think that is? It's a decomposition. That's right. Okay? So the last thing that we worked on last semester was balancing chemical reactions, correct? Okay? So what it is showing you is that if you had 2 moles of aluminum oxide, you have 4 moles of aluminum. And all that is just taking them big numbers from the chemical reaction that are just counting numbers, just like the inches and feet. That's all it is. It's just a number. Okay. And notice it says on the very bottom, for the decomposition of aluminum oxide, the appropriate mole ratio would be used as a conversion factor. Okay? So again, that doesn't mean anything to you right now, but will make more sense when we start applying this. All right. Page 301, where it talks about molar mass. Does that term sound familiar? Did we do that last semester? Of course, the answer was yes. Recall from chapter 7 that the molar mass is the mass in grams of 1 mole of a substance, going back to that sodium carbonate or sodium bicarbonate. The only thing we did would say, what's the percent composition of 80 grams of sodium in that sodium bicarbonate or sodium carbonate. Again, you're just dealing with one substance or compound. Here, you're going to be working on both sides of a balanced chemical reaction. Okay. So to solve reaction stoichiometry problems, you will need to determine molar masses using the periodic table. So we've used that all throughout last semester, and again, we'll be applying that here shortly. Okay. So let's go ahead and turn the page. And notice on page 304, I should have said turn 2 pages. It's talking about ideal stoichiometric calculations. And again, that's what we're doing on here. On pencil and paper, you're theoretically coming up with how much should be produced. And we'll do an activity where you take 2 substances and then convert them into a product and you make a prediction. Ideally on pencil and paper, it says you should get 9 grams of it, but you only produce about 7. You're never going to get the same amount that you predict on pencil and paper than what you actually do in the lab. And that's what this is talking about here. So we'll read through this and do a quick example, and then we'll be done for today. So, top of 304. The chemical equation plays a very important part in the stoichiometric calculations because the mole ratio is obtained directly from it. Solving any reaction stoichiometry problem must begin with a balanced equation. Chemical equations help us make predictions about chemical reactions without having to run the reactions in the laboratory. The reaction stoichiometry calculations described in this chapter are theoretical. We just said you theoretically should come up with this, but I guarantee you when we get to that, you're never going to produce the amount that on pencil and paper tells you should. They tell us the amounts of the reactants and products for a given chemical reaction under ideal conditions in which all reactants are completely converted into products. However, many reactions do not proceed such that all reactants are completely converted into products. Therefore, stoichiometric calculations allow us to determine the maximum amount of a product that could be obtained in a reaction, but do not require that reaction be carried out. Okay, so the only thing we want to continue is just a mole to mole problem. And notice you have sample problems. It shows you how to do them. So I'll let you read through them if you think that it's important, and that's fine. We just want to, let's say, spend a little bit of time on page 306 with one of the practice problems. So notice you're not always given that balanced chemical reaction. You have to be able to come up with that yourself. Okay? So there's two things. Keep that in mind. And also, from this point on, if you're dealing with oxygen, it's no longer 16 grams if it's by itself. It's what instead? Now, which would be 16. It's 32. Why is that? You're right. Yes, because remember, when these gases or halogens are by themselves, what does that mean you have to do? Say that again a little louder, though. Yes, you have to make them diatomic because they're by themselves. Now, when you combine that oxygen with another element, you may not need to put a 2 there. Maybe yes, maybe no. Okay, so in problem number 1, it says ammonia, okay, or NH3, is widely used as fertilizer in many household cleaners. How many moles of ammonia are produced when 6 moles of hydrogen gas react with an excess of nitrogen gas? Okay, so as we look at this, we can do some predictions, say the answer is 4. See, I get to do that because I got a column over here that says we should get 4. Which doesn't mean anything to you unless you know how to solve that type of a problem. So, what it's saying is this ammonia is a type of fertilizer, so we know that that's being produced. Okay? It comes from the reaction of nitrogen and hydrogen. And this is what we're just talking about. If you do this and stop there, anything you do beyond that is going to be probably going to be wrong. Okay? And the simple fix to that, and we started introducing the skeletal system in anatomy and physiology this morning. There's certain things that we want you to learn and correlate with physiology, but when it comes to the anatomical structure or the anatomy of the human body, it's just straight memorization. Okay? There's no way to get around that. You have to memorize. You get the humerus, and you have different types of structures on that humerus. It's just what you have to do to be successful with that. This is just one of the things that you have to do to be successful with this is, I don't know if you want to say memorize it, correlate it, whatever it is you have to do to remember that these gases are diatomic. Okay? So it's once we do that, well then, hopefully, it becomes a little easier. So, and then notice, you might say, well, if there's a 2 here, why isn't there a 2 over there? Well, this was needed to balance out the compound. This is one of those rare times, I think you could say, that it just looks, this is how chemists have always written this as NH3, because this has a -3 charge, and that's a +1. And of course, we learned that last semester. But that's how you write ammonia. Okay. So the next thing you're going to want to do is notice it says, okay, how many moles of ammonia? That's this. We don't know. Now, whether you write this setup like this, that's entirely up to you, what you feel most comfortable with. If you put this above here, fine. Okay. If not, okay, is there a chance you could make a mistake? Yes. Increased chance? Probably. Especially if you are working on this and you get interrupted with different, I don't know, distractions, if you want to call it that. And if you don't have that marked out, well, then you got to look back and say, oh, gosh, where did I leave off and what do I need to do? Okay? But it's saying how many moles of this ammonia are produced when 6 moles of hydrogen gas. So we're starting with 6 moles of this. Okay? So with this substance, we want to know how many moles of that are produced. Okay? And another aspect that you can get away with last semester is not showing your labels. In my opinion, if you carry that over here, the chances of making a mistake are going to be increased. It doesn't mean we're not smart. I would say it's, what you want to call it, laziness, maybe yes, maybe no, but you're just increasing the chance of not being correct. Okay, so the next thing you need to do with this equation is what? Notice we said with any stoichiometric problem, you have to start with a what type of reaction. It has to be balanced, okay? So, these come in pairs. This one's odd. So the best way to get that 3 to an even number is do what? Multiply by 2. So that gives us 2 nitrogens, 6 hydrogens. We've got 2 nitrogens, but only 3 here. So we need to get that up to a 6, so we put a 3 there. Okay? Now we've got our balanced chemical reaction. We have our setup. Now we can convert moles of this to moles of our unknown. That's of what we're looking for. So we've got 6 moles of hydrogen. And it's just good practice to keep putting that 2 behind there. And why would you want to do that? Think of maybe late in a basketball game. Okay? Let's say it's the first and second quarter. You take the ball. Who takes the ball out of bounds after a made basket? Whoever. Okay. So it's in the second quarter. There's still 4 minutes to go in the second quarter. Lots of game left. Okay. Your opponent makes a basket. Someone calls timeout. Okay. So you come back out on the floor. They're not putting a full court press on you. You're standing there. The official goes like this to you before he hands the ball. Goes like this. Why is he doing that? Yeah, because it was a made basket. The ball was not whistled dead. Well, it was on a timeout. But when you inbounds that ball again, since it was a made basket, you can run the baseline. Even though there's no one guarding you, even a blind-eyed baboon knows that you're not going to run the baseline, but it's just good practice he does this, is now there's 30 seconds left in the game, and it's a 1-point game. Same scenario. Someone made a basket, they call timeout. Are you always going to remember that you can run the baseline? Maybe not. Is an official always going to remember to tell you this? But if they keep practicing this throughout the game, what's the likelihood of them remembering it when it really counts? Pretty high, I would say. Okay? So my point is, when you keep this good practice up, you're going to increase your success rate. That's just what we're trying to pass on to yourself. Take it, leave it, do whatever. Okay? So, what we're doing with this, once you have it in moles, just like what we did last semester, that means you can change what you have into what it is that you're looking for. In other words, it's what we have in moles to what we're looking for in moles. Okay? So, how do we cancel? This is just a 2-step problem. Here's one. How do we cancel this mole out in our next step? You put it on the bottom. You put moles of hydrogen on the bottom. And we're changing what we have and we want to put it into what we're looking for, which is moles of ammonia. Okay? So we put mole of ammonia on top. Now, the last step is when you see a mole over a mole, that means you have to go back to your balanced chemical reaction and pick out the coefficients. Okay? And again, what's the coefficient for nitrogen? 1. What's the coefficient for hydrogen? 3, and then 2. So now we go back and we find hydrogen and ammonia, and we look in front and we see, oh, well, there is a 3 in front of the hydrogen, so we put a 3 here, and then we look over our ammonia and we see that there is a 2 there, and we utilize those coefficients in that manner. These cancel. We're in moles of ammonia, which is what we were looking for. So the next thing to do, take 6 times 2, gives you 12, and divide by what? And that gives you a total of what? 4 moles, just like we predicted. Okay? So again, 2 things, and I think it's important. Again, you can take this advice, you can leave it. Always put your little subscripts down here, and always put these labels on here. Take that advice, leave it. Again, it's entirely up to yourself. All right. Left middle, are we good? Okay. Left outside, or right outside, yes, left outside. Okay. Left middle, right outside, and middle. Okay. So we will work on another one of these tomorrow, and then put another step in there, a mole to a mass problem, which just means you're putting one more step in here. That's all that means. Okay, catch up to you next time.